Okay, I think we will do the quiz later at the end of this class. But now we continue our lecture first. And then we will do the quiz, I think around yeah, 2:30. So we continue to thank you for time. Sir, how many minutes do we get? Yeah, I think 30 minutes. 40 minutes. 30 minutes. 30 minutes. Okay, so today we'll discuss about kinetic theory of gas. Okay, yeah, in this chapter we'll discuss and then review about the Avogadro's number. Yeah. So Avogadro number we can symbolize by Na. In the theory kinetic of gas, relates the macroscopic properties of gas. And so this is the relation about macroscopic properties and microscopic properties. Yeah. Here we define 1 mole of a substance contains of Na. Na is Avogadro's number. This one is the elementary units, usually atoms and molecules, where Na is found experimentally to be 6.02 times 1023 mole per mole. Yeah. I mean, in 1 mole molecules or atoms, it consists of this number, 6.02 times 10 power 23 particles. So the mass of per mole M of a substance is related to the mass of an individual molecule of the substance by molar mass. M is M times Na. Yeah. Okay. This one describes about the mass of per mole, yeah, of a substance, and then M is the individual molecule of the substance. Yeah. I mean, if we have 1 mole, yeah, we can add total mass of molecules. For example, if we have a cube consists of gas, 1 particle of gas, it has mass M. Then if 1 mole is equal to number of Na, 6.03 times 1023. So we can multiply the total mass here. So total mass is the mass of 1 particle times this one. 6.02 times 1023. So the capital M, it means the total in 1 mole. What is mass of 1 mole? And then the number of moles N contained in a sample of mass M sample consisting of N molecules is related to the molar mass M
of the molecules of Avogadro's number Na. Yeah. So M here is the molar mass. So we can calculate 1 mole is the mass of sample mass divided to the time. That is molar mass of atoms or particles. Yeah. Okay, and then the ideal gas. Yeah. So we need to identify why an ideal gas is said to be ideal, and then what is the characteristic of ideal gas, and relate the ideal gas, constant R, and Boltzmann's constant K. Identify that the temperature in ideal gas law must be in kelvins. Okay. So remember that I think last week we have discussed about this equation. This is the equation for ideal gas. So ideal gas pressure times volume is nRT. P is the pressure, V is volume, N is the number of moles. R is the gas constant. T is the temperature in Kelvin. So remember that the temperature needed to convert to Kelvin gas. If we define this one, pressure times volume, and is the total of particles divided over the number. And A, and then times R times T. So here, the gas constant divided to Avogadro, and R divided A is equal to K. So this one is PV and KT. So we can use the equation of this one. The difference is R is the gas constant, but K is Boltzmann constant. Yeah. So K is Boltzmann constant, but R is the gas constant. The value of R is what? K for you take 1 joule per Kelvin for the gas constant, but K is Boltzmann constant. So PV is equal to NKT. So this equation is for ideal gas, right? Okay. Okay, remember for isothermal work done by an ideal gas, the work done by ideal gas is the isothermal constant is an artificial natural logarithm, yeah. Final volume divided to initial volume. So remember the PV gas. So in isothermal process, isothermal, the PV gas is like this. One is pressure and volume. And then the first point is the initial volume to final volume. So that's the expansion. I mean, the volume will be larger, and then the pressure will be slow. T initial and T final. Okay. So this one is the type depth for isothermal process, and for the work, we need to calculate the area under the curve. So the area under the curve, we can use integral form. Remember that PV is nRT, so P is equal to nRT divided by volume. And then, if you want to calculate the work, work is integral of initial volume to final volume. This one is the initial value and then final value. PdV, right? And you can convert from P is undoubtedly divided by volume. This one becomes integral volume to final volume, and RT divided by volume is PV.
since NRT is the constant, and we take the integral of 1 per v. So integral of 1 per v comes to natural logarithm. So this one. Okay. From this equation, we get that NRT is a constant, so we can take out from the integral. And integral of 1 per v. Initial volume to 5 joules. You remember, right? For integral of 1 per VdV comes to natural logarithm. This one and RT natural logarithm of the initial volume to final volume. That and RT 1 to final and other initial. This one and RT 1 to final divided to P. So this one is the work of isothermal process.
Okay, so the isothermal, we see here that from smaller temperature to larger temperature. Yeah. This one for 300 Kelvin, 310 Kelvin, and 320 Kelvin. Okay, so this one is along the isothermal. The gas has constant temperature, so the temperature not change. Yeah, but there is change of pressure and volume, right? So higher temperature will be higher pressure. This one, for example, if we take, yeah, for example, 500 Kelvin, yeah. But lower temperature will be here. For example, T is 100 Kelvin. Okay. And then pressure, temperature, and RMS speed. Yeah. RMS, it means that root mean square. This is related to root mean square speed and the average speed of particle. So we need to know that pressure is N times mass, PRMS degree volume. So this one is the speed of gas molecules affects pressure. How to get these equations? We need to understand about small particle. Okay. Yeah, this one is the pressure. N is small, and then M is molar mass. VRMS square divided to 3 volume. Yeah. Okay, so we can derive this equation by using like a cube, yeah. Rooms like cube. Okay, so for this one, can take notes from here. imagine if we have three-dimensional particles. Okay, three-dimensional coordinate system, and this one is, for example, X, and then Y, and then Z. So imagine we have a cube here. Okay, imagine we have a cube and then a particle inside the cube. Okay, for example, this one. So particle with mass m and velocity v. Okay. So it has component velocity sx. If we focus to momentum, so delta p at x-axis is equal to minus mass vx minus mass vx. So it will become minus 2 mass vx. This one is the change of momentum, right? Remember that P here is not pressure, but this one is momentum. Yeah. Momentum of particle at x axis. And then the force, F1. You know, force is the change of momentum divided to time, right? So this one is delta P at x position divided to delta T. Okay, this one is momentum. Okay. And then the force 1 times delta T equal to delta Px minus 2 mass Vx. So F1 minus 2m Vx divided to delta T. Okay, if we want to calculate the time that the particle, so the size of the cube is d, and then time is 2d divided to Vx. Okay, since they reflected. So here we will get that F1 minus 2m Vx divided to delta T. Delta T is 2d Vx. So it becomes minus mass Vx squared divided to d. So d is the size of the cube. Okay. And then the force of particle to the wall, imagine it's collide with the wall. So F1 on wall, this one is m divided to d. So if we have more particle, this one is only for one particle. So for all particle, it means that Vx1 square, Vx2 square, Vx3 square, and so on until Vxn. So the total or the average of the speed is Vx1 square plus Vx2 square until Vxn square divided to n. Okay, this one is the average of velocity. Yeah. And then we will get that the total square of the velocity, Vx1 square, Vx2 square, will Vxn square, n times V bar x square. Okay. So we get that force is equal to Nm divided to d Vx bar square. Okay. Vx bar square. Okay. Okay, remember that velocity is a vector. Yeah. So velocity is vector, that's v bar is the total of vx square, vy square, and vz square. So since we assume that vx, vy, and vz is equal, vx bar and then vy bar and then vz square is equal. So this one becomes 3 times of vx square. This is the average velocity square. Okay. And then vx bar square is 1 divided to 3 v bar square. Yeah. So we can substitute to these equations. Okay. So we get the force. The force is n divided to 3 and then m d v bar square. Okay. Okay. So if you want to calculate the pressure, so pressure is force divided to area. Force divided to d square. It becomes d and 3 and then mass per the cubic mv bar square. Okay. Okay. Any questions about this one? Yeah, this one is the pressure of ideal gas. Yeah. So we can calculate the average of the kinetic energy. Yeah. So by this relation, pressure is 2 divided to 3 n. This one is the volume. So the power 3 is volume. Yeah. Then, so how mv bar square? This one is the kinetic energy. Yeah. Average kinetic energy. Okay. So this one we get the pressure, right? And then what is the molecular interpretation of temperature? Yeah. So P here, P is pressure in Newton per meter square. And then V, this one is the volume, meter cubic. And then M is the mass of particle. Okay. Mass of particle or molecules. This one in kilograms. Okay. And then V bar, this one is average velocity. Yeah. The average velocity in meter per second. Okay. So since kinetic theory of gas is, we need to know what is the relation of macroscopic and microscopic properties. Yeah. So we know that the molecular interpretation of temperature. Yeah. So this one, molecular interpretation of temperature. Yeah. So from the ideal case, PV is nRT. Yeah. So this one is 2 divided to 3 n, and then half mv per square. We know that PV is equal to n k t. Yeah. So this one, we know that kt is equal to 2 divided to 3 half mv per square. So we get that the temperature is 2 per 3k half mv per square. Yeah. It means that the temperature will be proportional to average kinetic energy. Yeah. So by this equation, T is depend to average kinetic energy. Yeah. So the conclusion is temperature is proportional to average kinetic energy. Yeah. Okay. It means that higher temperature, the kinetic energy will be larger. Yeah. Okay, so by this equation, we know that the kinetic energy half mv bar square, it is equal to 3 divided to 2 kt, right? So this equation is later we will know, yeah, the derivation for PRMS. Okay. So this one is the average kinetic energy per molecule. Yeah. This one is the average kinetic energy per molecules. Okay, any questions for Jivan? So imagine that kinetic energy is the kinetic energy of one particle. Yeah. One particle, it has mass and then V. So V is Vxi plus Vyj and Vzk. Yeah. So there are three components, three vector components. It means that since the V bar square is equal to 3 Vx bar square. Yeah. So we will get that 3 divided to 2 mass V bar x square is equal to 3 per 2 kt. Yeah. So it means that half mvx bar square is equal to half kt. Yeah. Okay, so based this relation, by this relation, since Vx bar square is equal to Vy bar square, so the conclusion is half mvy bar square is also equal to half kt and then half m v vz bar square. Yes. Okay. Okay. So by this relation, and this one, it's called the theorem of equipartition. So this one is the theorem of equipartition of energy. Yeah. Okay. So for the theorem of equipartition of energy, it means that the component of kinetic energy at y, z, and y is x squared or x-axis equal to half k times t. So it means that its degree of freedom, yeah, its degree of freedom contributes half kt, to the energy of the system. Okay. Okay, it means this one is the kinetic energy and then theorem of equipartition. Its degree of freedom contributes half kt to the energy of the system. This is the theorem of equipartition. It means for translation, yeah, at x axis, y axis, and z axis. So the energy is half times k times t. Yeah. So what is the total translational? Yeah. Total translational kinetic energy of n particles or n molecules. So the total translational kinetic energy of n molecules, yeah, A translation is equal to n times half mv bar square. So if we have, for example, n molecules, and one molecules has a kinetic energy of mv bar square. One is total translational kinetic energy of n molecules. So imagine in a room, so many particles, right? So many particles. Yeah. And we assume that this one is ideal gas. Okay, so half mv bar square, this one, it means that n half mvx bar square plus half mvy bar square and then half mvz bar square. So this one is half kT. Also this one. Yeah. So the total kinetic energy is N times 3 divided to 2 kT. Yeah. So the total kinetic energy is equal to this one. Yeah. 3 divided to 2 N kT is equal to 3 N RT. Okay. So N is moles, yeah. The number of particle in mole, but the capital N, this one is the total of number of particle. Yeah. Okay, so remember that K is R divided to Na. R is the gas constant, yeah. 8.314 joules per mole Kelvin. And then N, this one is number of particle. Number of particles or number of molecules, and then N is number of moles. N is number of particle divided to Na. So Na is Avogadro number, right? Okay, so Avogadro number is 6.02 times 10^93. Okay, so this one is important question. The total kinetic energy, yeah. Okay, so the kinetic energy is half mass times V squared, right? So this one is equal to half mass V bar square is equal to 3 divided to 2 N or KB times T. So the V bar square is equal to 3 KT divided to M. Yeah. Or we get that this one is VRMS. So VRMS is equal to square root of this one. 3 KT divided to mass. So remember that M is mass for one particles. So this one is the root mean square velocity. Or root mean square speed. Okay. Okay, remember that K is N divided to Na. So we can change that PRMS 3R divided to Na times T times mass. So this one is molar mass, right? Molar mass. 3RT divided to molar mass. Okay. Okay. So VRMS, this one is root mean square speed. Yeah. But capital M is molar mass. This one in kilograms per mole. and then m is mass of particle. Okay. Kilograms. Okay, any questions about RMS speed? Yeah, so we get that VRMS is equal to 3 RT divided to molar mass. Okay. And then this one is the example for RMS speeds at room temperature for several gas, yeah. Hydrogen, helium, water, water vapor, and H2O, and then nitrogen, oxygen, carbon dioxide, and sulfur dioxide. So for the convenience, we often said that room temperature is equal to 300 Kelvin, equal to 27 degrees Celsius or 81 degrees Fahrenheit. That represent a fairly warm room. Okay, so for example, the hydrogen gas in room temperature and molar mass is 2.02, so the VRMS is around 1920 meter per second. So the VRMS is depend to temperature and molar mass. So higher or larger molar mass, it means slower RMS, VRMS. Okay, since VRMS is 3 RT divided to molar mass. Okay. So V is depends to square root of molar mass. Larger molar mass, it will be slower VRMS. Okay. Okay. Any questions about RMS speeds? Okay. Next, we discuss about translational kinetic energy, and we have verified. So the average translational kinetic energy, this one is 3 divided to kT. Yeah. We have verified before that this one, right? How we get 3 divided to 2 kT. This one. Since the theorem of equipartition is degree of freedom contributes half kT to the kinetic, to the energy of the system. Yeah. So we get that translation for translational kinetic energy is equal to 3 divided to kT. Yeah. At the given temperature T, all ideal gas molecules, no matter what their mass, have the same average translational kinetic energy, namely 3 divided to 2 kT. When we measure the temperature of a gas, we can also measure the average translational kinetic energy of its molecules. Okay, by this equation, we will know that doesn't matter of the mass. So different mass, the kinetic energy will be the same, since the kinetic energy of particles only depend to temperature. Okay, for example, a gas mixture consists of molecules of types 1, 2, and 3 with molecular mass M1 more than M2 and more than M3. Rank the three types according to the average kinetic energy and RMS speed. Yeah. So the kinetic energy will be same, but RMS speed will be different, right? So VRMS 3 kT divided to N. Yeah. Higher mass, so VRMS will be lower. Yeah. But for the kinetic energy, they equal. Okay. So kinetic energy 1 equal to kinetic energy 2 and kinetic energy 3. Yeah. Okay. That's why, since the kinetic energy is only depend to temperature, it is not depend to the mass of particle. Okay. So this one for ideal case. But for PRMS, still depend to mass of as one as higher still the highest level of factor 1 in for the loss. Then next is mean free path. Mean free path learning objective is identify what is meant by mean free paths and then apply the relationship between mean free paths to diameter of molecules and the number of molecules per unit volume. So the mean free path lambda of a gas molecule is its average path length between collision and is given by these equations, where n divided V is the number of molecules per unit volumes D, and D is the molecular diameter. Yeah. Okay, so in the figure, a molecule traveling through a gas colliding with another gas molecules in its path. Although the other molecules are also stationary, they are also moving in a similar fashion. Yeah. So this one is the graphic division of gas molecules. And then how about the distribution of molecular speed? So the distribution of molecular speeds it is the Maxwell speed distribution. Yeah. So the Maxwell speed distribution PV is a function that PV dV gives the fraction of molecules with speeds is the interval dV at speed V. So this one is the Maxwell speed distribution of oxygen molecules at T 300 degree Kelvin, and the speed distribution of oxygen 300 Kelvin and 80 Kelvin. Okay. Okay. So this one is average, probable, and RMS speeds of gas molecules. 3 measures of distribution of speeds among the molecules of gas. So V average, it's RT divided to PM. And then this one is most probable speed, yeah, and RMS speed. Okay. Okay, and then next is the molar specific heats and of an ideal gas. So if you remember last week we have discussed about adiabatic process. So there is the constant Cp and Cv, which is Cp is the molar specific heats at pressure constant. Yeah, molar specific heat at constant pressure, and then Cv is the molar specific heat at constant volume. Yeah. Okay, so next we discuss about molar specific heat of an ideal gas. So molar specific heat of an ideal gas. So the molar specific heat of an ideal gas, we remember the formula of heat. This one is mass C delta T. Okay. So we remember that the specific heat or the heat capacity, yeah, the heat capacity is mass times specific heat. Okay. So this one is the specific heat, right? Yeah. 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 3 to 13. Yeah. Okay. So this equation, we know that Q is equal to molar and then Cv delta T. Okay. This one is for constant volume. And then the heat for constant pressure and Cp delta T. And this one is for constant pressure. Okay. So Cv is the molar specific heat at constant volume. Yeah. Cv, we define that molar specific heat at constant volume. And Cp, this one is molar specific heat at constant pressure. Okay. So the internal energy, yeah. So the internal energy, remember that internal energy is the total of kinetic energy of gas. Yeah. This one is 3 to K, yeah, NKT, right? So it is equal to 3 divided to 2 nRT. Okay. So we know from the first law of thermodynamics, Q is delta internal energy plus W. So this one is the first law of thermodynamics, right? Okay. So this one is the first law of thermodynamics. So for the constant volume, the first one is the constant volume. We remember for the constant volume graphs, so the process will be like vertical. Yeah. This one is the pressure and then volume. So for example, from here to here. So delta V will be 0, and then W integral initial volume to final volume P dV also 0. So for the constant volume, since the W is 0 for monoatomic gas, we'll get that the delta internal energy is Q minus W, right? Q minus W, so W is 0. So the internal energy, this one is 3 divided 2 nRT will be equal to Q and CV delta T, right? Oh, sorry, this one is delta T. So we get that CV is equal to 3 divided to 2R. Yeah. This one is uh, for monoatomic gas. Yeah. CV will be 12.5 joules per mole Kelvin. Okay, so this one is for all monoatomic gas. Monoatomic gas, yeah, for example, is helium, only 1 atoms. So the formula of CV is 3 divided to 2R. This one is for constant volume. Okay. And then for constant pressure, okay. So for constant pressure, remember that Q is delta internal energy plus W. So we can draw the graphs of constant pressure. This one is pressure and then volume. So the pressure will be constant. Initial volume to final volume. Okay. So for example, the process from this one to this one. Yeah. So W is P delta V. This one is P final volume minus initial volume, right? So remember for the ideal gas, PV is nRT. Yeah. So P delta V is equal to nR delta T. Okay. Delta internal nRT. Okay. Okay, so this one, we will get that N CP delta T. Yeah. CP is 3 per 2 R. Yeah. And then this one is plus R. You get that CP is 5 divided to R. Okay. And before at CV is 3 divided to R. Okay. So CP 5 divided 2. Yeah. Okay, this one is the CP. CP is the constant pressure, molar specific heat at constant pressure. Okay. Okay, any questions about the kinetic theory of gas? Okay, and then we remember for adiabatic process. Yeah, but before we move to adiabatic process, we know the CP is 5 divided to R, and then this value 5 divided to R is 8.314. So the value of CP is 20.8 joule per mole Kelvin. Okay. And then we know gamma. Yeah. Gamma is the Laplace constant. Gamma is CP divided to CV. So this one is 5 per 2R and then 3 divided to R. So this one is 5 divided to 3, 1.67. So we need gamma for adiabatic process, right? So for adiabatic process, last week we have verified that adiabatic process PV power gamma is equal to constant. So it means that initial pressure times initial volume, power gamma equal to final pressure times final volume, power gamma. Yeah. Okay. So this one, and then we remember that PV is nRT. So we can say that P is nRT divided to volume. Yeah. So for this one, nRT initial divided to P initial gamma, and then nRT final volume final gamma, and then volume final. Yeah. So from this equation, we will get that the initial V initial gamma minus 1 equal to the final P final gamma minus 1. Okay, this one is for adiabatic process. Yes. Okay, any questions for adiabatic and then constant pressure and constant volume process? Yeah. The thermal process is the same temperature. Yeah. Okay, so the example for adiabatic process. For example, air at 20 degrees Celsius in a cylinder of a diesel. Diesel engine is compressed from 1 atm at volume 800 centimeter cubic to 60 centimeter cubic. Okay. So we know that gamma is 1.4. Assume that the air is ideal gas. So the question is, what is the final pressure and temperature? And what is the final pressure and temperature? Okay, so for this example, we can use the adiabatic formulation that Vi power gamma is equal to P final power gamma. Okay. Okay, so in this case that initial temperature is 20 degrees Celsius and then compressed to from 800 to 60, right? Okay, and the pressure is 1 atm. Okay, so the pressure is 1 atm. This one is the initial pressure. So we can calculate the final pressure is Vi power gamma, P final power gamma. Okay. So this one initial pressure is 1 atm, and then V final is, oh sorry, V initial is 800 divided to 60 power 1.4. Yeah. So the final pressure is 37.6 atm. Okay. So the pressure is much higher than initial pressure, right? The initial pressure is only 1 atm, but the final pressure is 37.6 atm. And then what is the temperature? The final temperature we can calculate by Ti Vi gamma minus 1 equal to T final gamma minus 1, right? So the T final is Ti V final gamma minus 1. Okay, so we can calculate the final temperature. The initial temperature is, this one is 20 degrees Celsius, so 293. 293. 0.4. It is around 826 Kelvin or 553 degrees Celsius. Okay. Okay, this one is the sample for adiabatic process. So the case is air at 20 degrees Celsius in cylinder engine. Cylinder diesel engine is compressed from 1 atm at volume 800 centimeter cubic to 60 centimeter cubic. Yeah. Okay. So for constant volume and specific heat of ideal gas, we have verified the molar specific heat at constant volume. Okay. So this one temperature indicates internal energy change for ideal gas at constant volume. So the red one is constant volume. The temperature increase is done without changing the volume. Okay. Sure. Then constant pressure or compression of ideal gas. Then degree of freedom. Okay. So the degree of freedom for molar and molar specific heats. Okay. This one is degree of freedom for monoatomic translation. There are 3 degree of freedom, but for monoatomic there is no rotational motion. Yeah. So the total degree of freedom is 3. So this one 3 divided 2R, and CP is 5 divided to 2R. Okay. Okay, so for degree of freedom, this one is the equipartition of energy. So the equipartition of energy, I mean that there are several degree of freedom since rotation and vibration. Imagine this one is x-axis, y and z-axis. Yeah, so for example, the particle is, in this case, there is the velocity and then rotation, right? So rotation along x and z axis. Yeah. So the internal energy, yeah. So internal energy is 3 and half kT. Yeah. 3 is for translation, since x, y, and z translation, plus 2 and half kT. This one caused by translation. And this one is caused by rotation, right? Okay. So translation and rotation. So internal energy for diatomic gas, this one comes 5 divided to N KT, okay, or this one equal to 5 divided to nRT. Yeah. Okay, any questions for equivalent energy? Okay. So we can calculate CV also. This one is, we know that the internal energy is CV times N dt. Yeah. So CV is the internal energy per N dt. Yeah. So this one is 1 per N ddt of internal energy is 5 to nRT. Okay. So we get that CV equal to 5 divided to R. Okay, 5 divided to R. So this one is for diatomic gas. Yeah. Different with before. Before is for monatomic gas. So Cp is R plus Cv, 7 divided to R. Yeah. So this one is Cp and then this one is Cv. That's why for our example before is for example oxygen, and oxygen is diatomic gas. So it means that Cp divided to Cv is 1.4. We'll construct gamma is Cp divided to Cv, 7 divided to 2 and 5 divided to 2. This one is 1.4. Okay, this one for diatomic gas. So that's why for diatomic gas, Cv, yeah, for example, oxygen here is 5 divided to R, but Cp is 7 divided to R. Now for polyatomic gas, Cv is 3 and then this one is 4. Yeah. Okay, so another example is vibration. Sure. So imagine that we have gas, yeah, X, Y, then Z. There is vibration by like spring, yeah. But another one is rotation at X and Z axis. So the total internal energy is 3. Yeah. Sorry, 3 and half kT. This one's for translation. And then for rotation is 2 and half kT. Also for vibration, 2 and half kT. Okay, so this one is caused by translation, and then rotation and vibration. So the total internal energy is 7 divided to and KT. Yeah. And RT. Yeah. Okay, we can draw the graphs like this. So this one is translation, and then rotation and oscillation, and 7 divided 2. Yeah, for example, is helium. Helium is monatomic gas, only translation. But oxygen, there are translation and rotation. But more complex system. Yeah. This one is polyatomic gas. Okay. Okay. For rotational and oscillatory motions begin at certain energies. Only translation is possible at very low temperatures, but higher temperature will be there are oscillation and rotation also. Okay. Yeah, then adiabatic expansion. So adiabatic expansion. So we know the graphs. The yellow one is isothermal process in the same temperature, but adiabatic is like this. Yeah. Okay, and we can take the summary for this chapter. We start from Avogadro number and the definition of kinetic theory of gas, right? This one is relates the macroscopic properties of gas to the microscopic properties of the gas. Then the ideal gas equation of state, temperature of kinetic energy, and then distribution speed. Yeah. Okay. Okay, any questions about the kinetic theory of gas? No. Okay. I think if there is no questions, we will prepare for the quiz. Then, like as usual, please put your back in the front of the class and